Probability gets more complex when we talk about more than one event occurring. And in order to understand how to work such problems out, we need to understand two main concepts. One is the idea of mutually exclusive events, and the other is the idea of independent events and how we treat each of those. So we'll look first at mutually exclusive events. So mutually exclusive events are those events that cannot occur at the same time. So a good example of this is if I toss a coin. The result can either be a head or it can be a tail. It cannot be both. If two events are mutually exclusive, then the probability of those two events A or B occurring is probability of A plus the probability of B. So the probability of one or the other occurring is the sum of the two probabilities. Let's look at an example of that. Let's go back to our pack of cards. What is the probability of picking a red queen or a black king from a pack of cards? So the probability of a red queen, there are two of those, that's 2 out of 52, and the probability of a black king is 2 out of 52. So the probability of a red queen or a black king is the sum of those two probabilities, or 2 over 52 plus 2 over 52, which equals 4 over 52. That was a very simple and straightforward example. You could easily have worked that out by, counting the number of red queens and black kings in the set anyway. But often, however, you will have no more information about the experiment than the probabilities that you're given, and this is when formulae like PA plus PB come in handy. Let's look at a different example now. A survey of cars passing a particular spot shows that the colour of the cars are, well, 25% are red, 30% are blue, 20% are black, 10% are green, and 15% are some other colour. So we can work out the probabilities from this. P of a red car is 0.25, and so on, all the way down the list there. So what is the probability of the next car being red or blue, green or black, green or black or blue? So here you don't know how many cars in total pass that spot or how many of each colour. You just are given the probabilities, and you're going to have to use those probabilities to work out the combinations that we have there. So first of all, the probability of red or blue. Well, the probability of red or blue is probability of red plus the probability of blue, and that's 0.25 plus 0.3, which gives us 0.55. Probability of green or black is the probability of green plus the probability of black, which is 0.2 plus 0.1, which equals 0.3. And finally, the probability of green or black or blue is the probability of green plus the probability of black plus the probability of blue, 0.1 plus 0.2 plus 0.3, which gives us 0.6. So if we didn't have that little formula, we wouldn't have been able to work out those probabilities. And also, of course, we wouldn't have been able to use the formula unless we were dealing with mutually exclusive events, which we are here. If a car is red, it can't then be blue or another colour. It's mutually exclusive. Let's look now at the idea of independent events. If two different experiments are independent, it means that the outcome of one event does not affect the outcome of the other. So a good example of this is if I toss a coin 2 times. If it comes down heads the first time, it has no effect on what's going to happen the second time. You might have heard the phrase that a coin has no memory, which is what we use to describe this concept. That is, those events are independent. So let's see what happens when we do actually toss 2 coins together. So what are the possible outcomes when we toss 2 coins? We've got coin 1 and coin 2. Let's throw them together, and the first set of outcomes we get are there, and then we throw them again, and we get another set of outcomes, and we throw them again and get another set of outcomes, and we throw them one more time and get a final set of outcomes. Now you can throw the coins all day if you like, but you'll find there's only 4 different ways that 2 coins can land. And if we look at this in a table with coin 1 across the top and coin 2 down the side, coin 1 can either be a head or a tail, and coin 2 can be a head or a tail. So if we look at the different outcomes as they occur above, we can see that the first outcome is head-tail. The second outcome is tail-head. The third outcome is head-head. And the fourth outcome is tail-tail. This kind of diagram is called a sample space diagram. It enables us to list all the possible outcomes, and we can use this to work out the probability of any of the outcomes that we see. So if we wanted to know, for example, what the probability of getting two heads, we can see there's only one way from our sample space diagram. There are four possible outcomes, only one of those ways is two heads. So the probability of two heads is 1/4, or a quarter. It's fairly clear that the tossing of two coins together is independent of each other. We also know that the probability of getting a head from any one coin toss is a half, because, you know, one side is a head, one side is a tail, it's going to land half-half. So if we put this into equation terms, we can see that the probability of a head and a head, in this case, is equal to the probability of a head times a head. Half times a half is a quarter. So for independent events, we get the equation that probability of A and B occurring is probability of A times the probability of B. Time for an example. We throw two dice together, two six-sided dice. We're going to draw a sample space diagram for the outcome, and then we want to know the probability of scoring 7, or we want to know the probability of scoring greater than 8. So let's draw the sample space diagram first. So we'll put dice 1 across the top of our diagram, and we'll put dice 2 down the side. Possible outcomes are 1 to 6 for each of them, and we put a little plus sign in the corner to remind us that we're going to add those numbers up. Let's put the numbers in row by row. First row is 2, 3, 4, 5, 6, 7. Second row 3, 4, 5, 6, 7, 8, and so on, all the way down to the bottom where we get 7, 8, 9, 10, 11, 12. So the highest score with two dice is 12. The lowest score is a 2. So the first question is, what's the probability of getting a 7? Let's look across there. We've got 1, 2, 3, 4, 5, 6 sevens occurring. So 7 can occur 6 times out of 36. Or we would simplify that to 1/6. What about... So look at part B now. Score of greater than 8. Well, here we're looking at the probability of the score is equal to 9 or 10 or 11 or 12. Now these are mutually exclusive events, so we can also calculate this as the probability of 9 plus probability of 10 plus the probability of 11 plus probability of 12. And we can see there the probability of 9 is 4 out of 36, of 10 is 3 out of 36, 11 is 2 out of 36, and of 12 is 1 out of 36. This gives a total there of 10 out of 36. Many board games rely upon you throwing two dice and getting the score. So it's worth knowing what the probabilities of each score are, because that might help you play the game. Certainly if you play the game backgammon, understanding different probabilities of different dice throws are critical to being a good player. You can sometimes defeat the luck that dice have by having a good understanding of the probabilities of each score occurring. It's also true that questions involving the throwing of two dice are quite a favourite of examiners. So make sure that you know how to draw that sample space and to have a good understanding of the probabilities involved here. Another favourite kind of question involves beads in a bag. Here's a very simple one. A bag has 20 beads in it. 5 are red, 5 are blue, 5 are green and 5 are black. One bead is taken out and the colour is noted. The bead is then replaced. This is repeated 3 times. What is the probability that all 3 beads that were taken out are red? Key to working out the solution to this is understanding that each bead selection is independent of the previous one. You've taken a bead out, you've put it back, you've shaken the bag, and then you've taken another bead out. which colour you took out the first time has no impact on what colour you take out the second time or the third time. So the probability of each colour is the same. There are 5 beads of each colour, so it's 5 over 20, or 1 in 4, a quarter. For independent events, the probability of x and y occurring is the probability of x times the probability of y. In this example, what that equates to is that the probability of red and red and red equals the probability of red times the probability of red times the probability of red, or 1 quarter times 1 quarter times 1 quarter, which is 1 over 64. Which intuitively you should recognise as correct. The chances of the same thing happening over and over and over again are usually quite rare. So the chances of taking 3 beads out in a row you would see as not happening very often, so 1 time in 64 sounds about right to me. So let's summarise the main points here. If 2 or more events A and B are mutually exclusive, then the probability of A or B occurring is the same as the probability of A plus the probability of B. If 2 or more events are independent, i.e. they don't affect each other, then the probability of A and B occurring is the same as the probability of A times the probability of B. You need to remember those two things. You also need to make sure you're familiar with probability questions involving throwing of 2 dice and of packs of cards and tossing of 2 coins, 2 or more coins. Those are favourites with examiners. Particularly favourite is the idea of taking beads out of a bag, and we'll look at those as an example when we look at the idea of probability trees.